Welcome back to The Deep Dive. Today is Wednesday, February 18th, 2026.
2026.
Yeah.
It feels strange saying it, but here we are.
It really does. And if you're tuning in today, I'm going to guess a few things about your current situation. You're probably looking at a project timeline that is, shall we say, a very aggressive shade of red. Flashing red. You've likely got a coffee next to you that's been cold for at least 2 hours. And you are fundamentally trying to figure out how to certify a vehicle in a world that looks nothing like it did even 5 years ago.
It's a completely different landscape. We're not just talking about a new model year. We are living through, and this is not an exaggeration, a fundamental inversion of the physics of how vehicles operate.
That's the perfect way to put it. Now, usually on this show, we grab a bunch of articles, maybe a white paper, and we talk through them.
Yeah, we break it down.
Today, we're doing something a little different. Given the sheer complexity of the source material we have in front of us, we're going to role play a bit. We're putting on the metaphorical expensive suits. Today, we are acting as your senior technical strategy consultants.
Which means you, our listener, you're the client. You're the chief engineer, you're the head of homologation or the EMC lab manager at a major OEM or a tier 1 supplier.
And you've hired us to come in, stand in front of your boardroom, and frankly, make sense of the chaos.
Chaos is a good word for it.
The brief you've given us is, on the surface, very simple. The execution, however, is, well, it's terrifying.
It is.
You've asked us to deliver a top-down MECE strategic report. That's MECE. All about global automotive EMC technology for the 2026 landscape.
And for anyone who hasn't had the pleasure of living in a management consulting bullpen, MEC stands for mutually exclusive, collectively exhaustive.
No overlaps, no gaps, just a clean, comprehensive framework.
The goal here is to give you a structure you can act on. Because right now, the automotive industry is just drowning in noise. I mean, that both literally from the cars themselves and, metaphorically.
Yes, the signal-to-noise ratio is terrible right now. So our core thesis for this report is pretty stark.
It is.
The era of EMC as a static compliance checklist is over. It's dead.
Completely. We are done with the days of building a car, finding a problem, and then asking the EMC engineer to, sprinkle some magic ferrite beads on the wiring harness to pass a test.
Oh, I've been in those exact meetings. The Band-Aid phase of engineering. You're 2 weeks from the start of production, the radio is buzzing, and everyone is just praying that a clamp-on filter is going to fix it.
And you know what? For a long time, it actually worked. Or it worked just enough to get you past the certification gate.
It did.
But today, in 2026, EMC is a core architectural pillar. It's not an afterthought. It is a dynamic, high-voltage, system-level architecture issue.
And more than that, it's a critical path for vehicle safety. We have to hammer this point home. If you fail an EMC test today, you're not just dealing with some static on an AM radio that, let's be honest, nobody listens to anymore.
Right. It's not a customer comfort issue.
Not at all. You are dealing with a vehicle that might slam on its emergency brakes on the highway because it drove past a 5G cell tower.
That is the absolute nightmare scenario. And it's not science fiction. It is a real, quantifiable risk that we have to design for.
So over the next hour or so, we're going to unpack exactly why that is. And to keep this MECE, to keep it clean, we've structured this entire strategic report into 4 distinct, non-overlapping pillars.
Yeah. Okay, let's lay out the roadmap. Pillar 1 is all about the source of the problem, the physics of the new powertrain. We're going deep into the interference storm being created by 800-volt systems and this universal shift to silicon carbide.
Pillar 2, we move from physics to politics. We're calling it the regulatory battlefield. It's about the growing split, the geopolitical divergence between the European gatekeepers with their regulations and the Chinese standard setters.
Then Pillar 3 is about the money. Infrastructure strategy. It's the huge capital expenditure headache. Do you build a massive fixed lab or do you try to put your test equipment on wheels? The fixed versus mobile dilemma.
And finally, Pillar 4 brings it all together in the process revolution. This is about how we stop testing physical cars and start testing digital twins. How we shift left to manage the risks of the software-defined vehicle.
It's a full roadmap, from the silicon die all the way up to the cloud. So let's open the briefing book. Pillar 1.
Pillar 1, the physics of the new powertrain. Let's just set the stage with some baseline data. It's early 2026.
Right.
Global EV sales share is now pushing, about 27.5%?
Roughly, yeah.
Here.
And climbing fast. And battery demand has crossed the 1 terawatt-hour threshold. The momentum is just undeniable.
It is. The internal combustion engine is, of course, still with us. But in terms of new R&D, new platform development, it's a legacy asset. The focus has shifted.
And that shift has changed the nature of our emissions problem. If
Yeah.
you look back at the 2010s, the big emissions scandal that defined that decade was chemical.
Right. NOx, CO2, particulates.
It was all about what came out of the tailpipe. But here, in 2026, the primary emission we're fighting is electromagnetic. We've started calling it the emissions of the future.
I like that framing. We've traded visible exhaust fumes for invisible waves of energy. And the main culprit seems to be the very same technology that's making these cars viable in the first place.
That's the irony. It's the wide bandgap semiconductor.
The double-edged sword of efficiency.
Precisely. To get the kind of range that customers actually want, that 400 or 500 mile benchmark, and to get the charging speeds they
About
demand.
10 minutes to get 200 miles, promise.
Exactly. To do that, we had to abandon traditional silicon IGBTs in our inverters. We had to move to silicon carbide SESI, and in some applications, gallium nitride or GaN.
And these are the chips, the switches, that take the DC power from the battery and chop it up into AC to feed the motor, and they are staggeringly efficient.
Oh, incredible. We're talking well over 98% efficiency in some cases. They're marvels of material science. They have a massive breakdown field strength, which lets them handle much higher voltages in a smaller, thinner package.
But there's always a but.
There is always a but, and here it is. To achieve that efficiency, they have to switch on and off at almost unimaginable speeds.
Okay, let's get specific. The report mentions a key metric, DVDT, change in voltage over change in time.
Yes. And with modern cyclical converters, we are seeing DVDT values that exceed 50 volts per nanosecond.
Okay, let's pause on that number for a second because it sounds abstract. 50 volts per nanosecond. What does that actually mean?
It's electrically violent. A nanosecond is the time it takes light to travel about a foot. So imagine the voltage in your system going from 0 to, say, 400 volts in the time it takes light to cross a room.
It's like an instantaneous vertical wall of voltage.
It's a hammer blow, electrical sledgehammer. And every time that switch flips, thousands of times a second, this incredibly steep voltage front hits everything it's connected to.
The parasitic inductances and capacitances.
Exactly. The little bits of inductance in your cables and your bus bars and the motor windings themselves, things you could mostly ignore with slower silicon switches. But this steep gradient excites them. It's like striking a bell. It causes them to resonate, to create high-frequency ringing.
So instead of the nice, smooth waveform we want, we get this jagged, messy, oscillating signal writing on top of it.
A noisy mess. You're trying to create a clean sine wave to drive the motor, but at every switching point, you get this burst of high-frequency garbage. And that garbage is noise. It's RF interference that stretches well into the megahertz range with very significant amplitude.
And we're not just switching faster, we're switching with more force. The whole industry is moving from 400-volt architectures to 800-volt.
And this is where the physics really starts to punish you. All the data we're seeing shows that an 800-volt system generates common mode noise that is somewhere between 6 and 10 decibels higher than an equivalent 400-volt system.
And we have to remember, decibels are a logarithmic scale. 6 dB isn't a small increase.
No, 6 dBA is a doubling of the amplitude. So you've moved to a system that is fundamentally physically a much louder source of noise. And that noise is ringing at much higher frequencies than we've ever had to deal with before.
And all that noise has to go somewhere. I want to dig into one specific consequence you mentioned, because I think a lot of our listeners, especially those on the mechanical side of the house, might not connect these dots. Let's talk about bearing currents.
Yes. This is a critical failure mode. The technical term is EDM, electric discharge machining.
Which is something you usually do on purpose in a factory. You don't want it happening spontaneously inside your e-motor while someone's driving down the road.
Absolutely not. But it is. Here's what's happening. That hot VVDT, that super steep voltage front from the inverter.
The sledgehammer.
That sledgehammer pulse couples capacitatively from the stator windings across the air gap to the rotor. The voltage starts to build up on the rotor shaft itself.
Okay, so the shaft is now electrically charged.
Right? And electricity always wants to find a path to ground. The easiest path to ground from the spinning rotor is through the bearings, into the motor housing.
But the bearings are full of grease, and grease is an insulator.
It's a dielectric, yes, but it has a breakdown voltage. As the potential on that rotor shaft builds and builds, it eventually gets high enough to exceed the breakdown voltage of that thin film of grease.
Zap.
Zap, you get a micro arc. A tiny spark literally jumps through the grease from the bearing race to one of the balls and then from the ball to the outer race.
And every one of those tiny sparks is like a tiny lightning strike pitting the metal surface.
It is. It blasts a microscopic crater in the polished surface of the race. Over millions of cycles, this creates a distinctive pattern called fluting. It looks like washboarding. You are literally machining the bearing while the car is in motion.
And that leads to...
First, acoustic noise. A whine that wasn't there before, then vibration, and eventually catastrophic seizure of the bearing.
So a core EMC problem, an electrical noise issue generated by the inverter, manifests as a warranty claim for a completely seized motor at 20,000 miles.
That is the strategic insight right there. If you're a chief engineer, you cannot afford to think of EMC as just the radio problem. It is a fundamental powertrain durability and reliability problem.
Okay, so if the physics of silicon carbide are this hostile, what's the mitigation strategy? How do we tame this beast?
We're seeing a complete and total overhaul of filter technology. The old school wound wire chokes with big standard ferrite cores. They're just not cutting it.
Not.
Couple of reasons. They saturate too easily under the high currents, and more importantly, their frequency response just falls off a cliff right in the frequency bands where sync noise is at its worst. They're the wrong tool for the job.
So what are we buying in 2026? What's the new tool?
Two big things. First, a move to planar magnetics. Instead of winding a piece of wire around a donut-shaped core, we're embedding the inductor or transformer windings directly into the layers of the printed circuit board.
So it's a flat 2D component instead of a bulky 3D one.
Right. It's incredibly compact. It's highly repeatable from a manufacturing standpoint, and it has much, much lower parasitic capacitance and inductance. It's just a cleaner component for high-frequency work.
And the second thing?
We're switching our core materials. Standard ferrite is being replaced by nanocrystalline cores.
Nanocrystalline? That just sounds expensive.
It is an investment. I'm not going to sugarcoat the BLOM impact. It is significantly more expensive than a comparable ferrite core.
So what's the payback? Why spend the money?
Performance. In that critical 50 to 100 kilohertz range and extending up into the low megahertz, nanocrystalline cores can perform 3 times better than ferrite. They have a much higher permeability.
Which means you can get the same amount of noise attenuation from a much smaller, lighter component.
Exactly. And maybe even more important is the thermal performance. Ferrite has a really nasty habit of losing its magnetic properties as it gets hot. It's called the Curie temperature issue.
And under the hood of an EV running at full power, things get very hot.
Very hot. An 800-volt system running at 100 degrees Celsius. A ferrite core might just give up. It stops being a filter. Nanocrystalline is vastly more stable at high temperatures. It keeps doing its job.
So the strategic recommendation coming out of Pillar 1 is pretty clear. You have to pay up for the advanced filter materials. If you try to value engineer your inverter filter with cheap ferrite on a sickie system, you're not just going to fail EMC, you might be buying back motors.
You are going to fail. It's a question of when, not if. And you will likely be footing the bill for a lot of motor replacements when those bearings disintegrate.
Okay, that's a sobering look at the physics. Let's move to Pillar 2, the regulatory and standards battlefield. Because it's one thing to design a car that works, it's a whole other challenge to design a car that you're legally allowed to sell.
And this is where the strategy becomes geopolitical. Because in 2026, to get a car certified for global sale, you have to navigate 2 dominant and increasingly divergent forces.
And who are they?
On one side, you have the traditional gatekeeper, that's Europe and the United Nations, through the ECE regulations. On the other side, you have the new standard setter. And that is, without a doubt, China.
Let's start with the gatekeeper, the familiar one. UN Regulation 10.07. This has been the Bible for global homologation for a long time.
It has. And the R10.07 amendment, which became fully effective in June of 2025, really changed the game. If you want to sell a car pretty much anywhere outside of North America and China, Europe, Japan, Korea, Australia, you have to pass this.
And the single biggest change, the headline, is the frequency expansion.
It's massive. We used to test up to, what, around 2 gigahertz, maybe 2.5 in some cases?
Right.
Our 10.07 officially raised that upper limit to 6 gigahertz.
That's a huge jump. More than double. Why? What's living up there in the spectrum that they're so worried about?
Our entire modern wireless life. You've got Wi-Fi 6E, you've got the new 5G new radio bands, you have ultra-wideband or UWB, which is what your fancy digital phone key uses to unlock the car. All of that operates in that 2 to 6 gigahertz space.
So the concern is that the car's electronics could interfere with your Wi-Fi Or worse, that a strong 5G signal could interfere with the car's systems.
Both. It's a two-way street. But for the engineer who has to make the car pass, the implication is less about the services and more about the physics of the wavelength.
Okay, explain that.
At 2 gigahertz, the wavelength of the signal is about 15 centimeters. It's, about the length of your hand. You could have a small gap in the car's shielding, and that 15-centimeter wave is just too fat to fit through it efficiently. It mostly reflects off.
But at 6 gigahertz?
At 6 gigahertz, the wavelength is only 5 centimeters.
Tiny.
It's tiny. Suddenly, a 5-centimeter gap, like the seam between a plastic bumper and the metal body, or an imperfect seal around the trunk lid, that's no longer a small leak. For a 6 gigahertz wave, that gap is a massive, gaping hole.
It's a perfect slot antenna.
It is a perfect antenna. It will radiate noise out, or it will channel external noise in with incredible efficiency. So the job of sealing the vehicle has become an exercise in microscopic precision. You can't just have a metal cover. You need conductive gaskets. You need continuous mating surfaces every few millimeters. It's a different world.
And it's not just the frequency. The report says the test methodology itself is changing. I'm seeing reverberation chambers. This feels like a major departure from the classic anechoic chamber we all know.
It's a fascinating shift in testing philosophy. For decades, the gold standard was the anechoic chamber.
The room with the big blue spiky foam cones on the walls.
Right, designed to absorb all reflections to create a free space environment. You'd put the car in, you'd point a big antenna at it, and you'd blast it with a signal from one direction.
Simulating a radio tower, for example.
Exactly. But that's not the real world. In the real world, radio waves aren't coming from one clean direction. They're bouncing off buildings, off other cars, off the road surface. You're driving through a soup of signals from all angles.
So the reverberation chamber tries to replicate that soup.
It does. A reverb chamber is the opposite of an anechoic one. It's a room with highly reflective metal walls, no foam. And inside, it has these huge, slowly rotating metal paddles. We call them stirrers.
Stirrers. Okay, paint a picture for me.
Imagine a giant, oddly shaped metal fan blade, maybe floor to ceiling, in the corner of the room. As this thing turns, it continuously changes the boundary conditions of the room. It takes the signal you're injecting and just bounces it around chaotically from every possible angle.
It stirs the field.
It creates what's called a statistically uniform field. The key takeaway is this. The car isn't getting hit with a clean wave from the front or the side. It's being bathed, completely immersed in RF energy from every conceivable direction at once.
That sounds like a much tougher test. It sounds like it would find weak spots you'd never see with a directional antenna.
It does. A directional antenna might miss a poorly shielded cable that's hidden behind the engine block or tucked under a seat. The reverb chamber will find it because the energy gets everywhere. It's a much more thorough way to stress the entire system.
Incredibly thorough, and probably incredibly frustrating if you're the engineer whose design is failing.
It can be. But there's an upside. The tests are often much faster. And that brings us to the other huge methodological change in R10.07, the formal acceptance of FFT.
Fast Fourier transform.
Yes. For decades, the rules required a swept scan. Your test receiver had to tune to one frequency, wait, measure, then step to the next frequency, wait, measure.
I've watched those scans. It took hours to cover the whole spectrum.
Hours and hours of expensive chamber time. R10.07 now fully allows the use of FFT-based receivers, which can capture and process huge chunks of the spectrum all at once. It reduces the scan time for emissions testing from literally hours down to minutes.
So it's a big capital investment in the new receiver, but the payback in reduced chamber time is massive.
The ROI is usually well under a year. It's a no-brainer.
Okay, let's pivot now to the other major force you identified. Force 2, the Chinese leadership. This feels like a counterintuitive idea for a lot of us who grew up with regulations flowing from Europe or the US.
It's a mental model we have to update. In the world of electrified powertrains, China is no longer a follower. They are defining the standards. They have the sales volume, they have the manufacturing scale, and they have more real-world data than anyone else.
And they got tired of waiting for the international bodies to catch up.
Exactly. A perfect example is the standard for e-axles. That's GBT 18655-2025.
And the e-axle, just to remind everyone, is that highly integrated unit. Motor, inverter, and gearbox, all in one compact block.
Right. The problem was the main international standard we use for component testing, CISPR 25, is a bit vague on how to set up a test for one of these things. It doesn't give you precise instructions on how to arrange the drive shafts or the cooling lines or exactly where to place the measurement antenna.
And in the world of EMC testing, vagueness is the enemy. It kills repeatability. My test in a lab in Germany should produce the same result as your test in a lab in Shanghai.
But with the old standard, it often didn't. You'd get different results depending on the test setup. So China went ahead and wrote their own.
Yeah.
GBT 11, 8 and 6, 5, 5, 10, and 25 provides exact millimeter-perfect definitions for the geometry of the drive shafts, the torque, the speed.
It's a recipe.
It's a precise recipe. But here is the killer detail, the thing that every one of our clients needs to pay attention to. They added a vertical measurement antenna position.
Vertical. We almost always measure from the side horizontally.
We do. But the Chinese engineers, by analyzing their field returns, found something crucial. They found that a common failure mode was noise leaking upwards from the E-axle.
Upwards? How?
Through the seals on the casing, or more often radiating directly off the high-voltage connectors, which are usually on the top surface of the inverter.
And the CISPR standard, with its side-on antenna, would miss that completely.
It was blind to it. The antenna was looking at the side of the box, but the leak was coming out of the top. The Chinese standard puts a measurement antenna directly above the unit, looking straight down. It puts the eye right where the leak is most likely to be.
So as a global OEM, what's the strategic play here? If I'm not planning to sell a particular model in China, do I just ignore this? Say, well, it's a U.S. market car. I don't need to worry about GBT.
That would be a massive strategic error. Our recommendation in this report is unequivocal.
Yeah.
Even if you are never, ever going to sell a single car in China, which is a pretty unlikely scenario anyway, you should adopt the GBT 19655 test setup for all of your internal R&D and validation.
Because it's just a better test. It's closer to the physics.
It's a more rigorous test.
Yep.
It will catch failure modes that the legacy CSPR test will miss. The bottom line is this. If you can pass the GBT test, you will fly through the CSPR test. But the reverse is not true.
And you avoid the nightmare of launching a car and then discovering the E-axle is radiating noise straight up into the infotainment system or the telematics control unit that's sitting right above it in the chassis.
You find the problem in your own lab, not when the customer complaints start rolling in. It's about de-risking your entire platform.
That is a classic top-down insight. Don't just follow the letter of the law for the market you're in. Follow the law of physics. And right now, the Chinese standard is a better reflection of that physics.
Precisely.
Okay, this brings us logically to Pillar 3. Infrastructure and capital strategy. We know what we need to test for. But building the facilities to do this testing is an eye-wateringly expensive proposition.
It is. The central dilemma that every lab manager and VP of engineering is wrestling with in 2026 is what we call the fixed versus mobile asset problem.
Let's break that down. A full vehicle anechoic chamber is a massive capital investment.
Millions and millions of dollars. You have the shielded room, the ferritiles, the absorbers, the high-power amplifiers, the specialized ventilation. The single most expensive thing you can do with that multi-million-dollar asset is have it sit empty.
Right. And it sits empty during setup time. While your technicians are inside, wheeling in the dyno, bolting the motor to a test pallet, hooking up dozens of cables and coolant lines.
That downtime is what kills your ROI.
Right.
It murders your test throughput.
So the industry is rapidly moving toward a hybrid asset strategy to combat this. It basically breaks your lab into two types of players.
The mobile test bed and the fixed high-performance rig.
Exactly. Let's talk about the mobile one first, the flex player.
Okay.
Imagine a standardized heavy-duty pallet on wheels. It has everything you need for a component test. The e-motor, the battery simulator, the cooling system, all the control hardware pre-mounted and pre-wired on this single mobile unit.
And the key is that you do all the setup work on this pallet outside of the expensive chamber. Precisely. You have a dedicated, low-cost prep area. Your techs can take their time, get the coolant hoses connected just right, calibrate all the sensors, run initial diagnostics.
All while the anechoic chamber is busy running a completely different test on another project.
Exactly. Then, the moment the chamber is free, you roll the old test pallet out, you roll the new one in, you connect one master plug for power and data, and you are ready to start testing in under 15 minutes.
It's about maximizing the beam time, to borrow a phrase from particle physics, maximizing the time the chamber is actually acquiring data.
That's the whole game. This mobile approach is perfect for R&D, for rapid iteration, for component-level work.
But it has its limits. That brings us to the heavy player, the fixed high-performance rig. This is for testing those big integrated e-axles we were just talking about.
These are absolute monsters. You can't put these on a mobile pallet. You're talking about systems that require two separate load machines, two dynamometers that need to absorb and dissipate over a megawatt of power combined
A megawatt.
and handle tremendous amounts of torque. This kind of equipment needs to be bolted to a massive, isolated seismic mass in the floor of the chamber. It's a permanent installation.
And there's a physics problem here that I think people often underestimate. If you are running a megawatt of power inside a sealed, shielded, insulated room,
You're not just running a test, you're building a very efficient oven. The waste heat is enormous. You need massive amounts of liquid cooling and high-volume air handling.
but you can't just cut a big hole in the side of your shielded chamber for a ventilation duct or a water pipe. That's an EMC nightmare.
It's a giant leak. It's like leaving the door wide open. So how do you get the air and water in and out without letting the RF noise follow?
Waveguides.
Exactly. Specifically, honeycomb waveguides. These are basically bundles of small metal tubes packed together like a honeycomb. Air can flow through them, and non-conductive pipes can pass through them.
But the electromagnetic waves, if their wavelength is larger than the diameter of the individual tubes, they can't propagate. They get cut off.
It's a filter, a physical filter. It lets you solve the thermal problem without compromising the shielding integrity of the room. It's brilliant.
And it's not just the room. The test equipment itself, the dyno that's providing the load, it has to be. Well, the report calls it invisible.
Electromagnetically invisible. This is probably the single hardest specification for the equipment supplier, like AVL, to meet. Think about it. Your dynamometer is itself a powerful piece of electrical equipment with its own inverter and control systems.
If that dyno is generating its own electronic noise, how on earth can you tell if the noise you're measuring is coming from the car you're testing or from your test rig?
You can't. Your baseline measurement is contaminated. You're chasing ghosts.
So what's the spec? How quiet does the dyno have to be?
For a 2026 spec dyno, like the AVL Road Sim, the requirement is that its own radiated emissions, its background noise floor, must be at least 13 decibels lower than the CSPR12 limit for the vehicle itself.
Wow, that is incredibly quiet. It's like trying to build a jet engine that only whispers.
It's a huge engineering challenge. And then on the flip side of that coin, you have immunity. The dyno can't just be quiet. It has to be incredibly tough.
It has to be able to survive the test itself.
Yes. When we're doing an immunity test and we blast the vehicle with a simulated radar pulse at 1200 volts per meter, the dyno controller cannot have a single glitch.
Because if it does,
If the dyno loses control of a 1,000 horsepower e-axle that's spinning at 20,000 RPM because it got zapped by a radar pulse, you have a catastrophic, explosive mechanical failure inside a sealed room. The shaft shears, parts fly. It is a massive safety risk.
and that brings us to the human safety element. The report is very clear on this. No more human drivers. We need robots.
This has become completely non-negotiable. You simply cannot ask a human test driver to sit inside a vehicle during a high field strength immunity test. A field of 200 volts per meter can induce currents in the human body. It can raise your body temperature. It can interfere with medical implants like pacemakers. It is fundamentally unsafe.
So we put a robot in the driver's seat to push the accelerator and the brake?
But you can't just use any robot. If you take a standard electric industrial robot, like a KUKA arm, and stick it in the car, you've just introduced a huge new problem.
Its own motors, its own wiring harness. They're made of metal. They will reflect and scatter the test field.
It completely destroys the uniformity of the field you're trying to create, and the robot's own electronics will generate noise. You ruin the very test you're trying to conduct.
So what's the solution?
Pneumatic robots. Robots that are powered by compressed air.
So they're made of plastic and they're moved by air hoses.
Essentially, yes. No metal structures, no electric motors, no wires. They are completely transparent to the electromagnetic field. They compress the pedals with precise force using air actuators, and those air lines run back through those same waveguides we talked about earlier. It's an incredibly elegant solution that solves the safety problem without creating a new physics problem.
Okay, that covers the physical world. Let's move to the final and maybe most revolutionary pillar. Pillar 4, the process revolution. We've talked physics, we've talked regulations, we've talked about the labs. Now let's talk about time. The shift left imperative.
Shift left is a term that got popular in the software world, but for automotive EMC in 2026, it is absolutely existential.
What do we mean by shift left?
It means moving your testing earlier in the development timeline. To the left on a Gantt chart, Traditionally, EMC testing happened very late. You had to wait until you built a full working prototype, a mule car, then you'd put it in the chamber, you'd find 100 problems, and you'd enter this mad scramble to fix everything.
The panic phase, the sprinkle on the ferret deeds phase we talked about.
Exactly. But in 2026, with development cycles shrinking from 48 months down to 24 or even 18, that physical prototype just arrives too late in the process. If you find a fundamental EMC issue on your first physical prototype, like a main cable harness being routed incorrectly,
You're dead. You're 6 months behind schedule on day one. You can't retool the body shell. You miss your start of production date.
you miss the date. The program fails. So the imperative is we have to find and fix these problems before the car even exists in physical form.
Yeah.
And that leads us directly to XDT executable digital twins.
This is the real game changer. And we're not just talking about a 3D CAD model to check for mechanical clash.
No, this is a full physics-based simulation of the vehicle's entire electromagnetic environment. We're using sophisticated software tools to build a virtual model of everything. The parasitic inductance and capacitance of every single wire in the harness, the layout of the PCBs, the switching logic of the SiC inverter, the antenna patterns, all of it, running in a massive simulation on a computer cluster.
But how accurate can that really be? EMC is notoriously difficult to simulate because, everything affects everything else. The slightest change can have a huge impact.
The accuracy has gotten breathtakingly good. The latest validation studies we're seeing from 2026 are showing a correlation between the simulation and the physical measurement that is within 30 microns for things like cable positioning.
30 microns, that's less than the width of a human hair.
It is. We can now run a simulation and predict with very high confidence that if you route this specific high-voltage cable 2 centimeters closer to that sensitive sensor wire, it will cause a radiated emissions failure at exactly 101.3 megahertz.
And you can know that 9 months before the first piece of metal for the prototype has even been stamped.
That's the power. It saves millions of dollars in tooling changes and prototype respins. It creates a virtual build, virtual test loop. You can iterate on the design 1,000 times in the virtual world, optimize it for EMC performance, and only then do you commit to building the expensive physical hardware.
But the report highlights a new threat here, one that emerges after the car is built, the SDV threat, the software-defined vehicle. And I have to say, this part of the report scares me more than any of the hardware issues.
It should. This is the sleeping giant of EMC compliance. For 100 years, we thought about EMC as a static hardware problem. The shielded box, the filtered connector, the braided cable. Once you built the car, that hardware's fixed. The EMC performance should be stable for the life of the vehicle.
But in a software-defined vehicle, the car's fundamental behavior changes every single time you push a software update.
Bingo. Let's walk through a scenario. You buy a brand new EV in 2026. It's great. It passed every single EMC regulation in the world with flying colors. It's parked in your driveway.
Okay.
6 months later, the manufacturer's software team in Silicon Valley comes up with a clever new algorithm. They push an over-the-air, an OTA, update to your car while you sleep. The release notes say this update optimizes the inverter efficiency to give you an extra 5 miles of driving range.
Sounds great. I want those 5 miles. What's the problem?
The problem is how they got that efficiency. To get it, the new software slightly changes the pulse width modulation, the PWM, switching frequency of the inverter. Or maybe it adjusts the dead time, that tiny fraction of a second where both switches are off to prevent a short circuit.
It changes the rhythm of the electrical sledgehammer.
It changes the entire harmonic structure of the noise coming from the inverter. Suddenly, a resonance in the system that wasn't being excited before is now being hit with its resonant frequency, and it starts to scream, electromagnetically speaking. The entire EMI profile of your car has just changed.
And a car that was perfectly compliant when it left the factory is now non-compliant sitting in my driveway.
Overnight. Or even worse, what if that new switching harmonic just happens to land on the exact frequency used by a critical safety sensor?
Like an ABS wheel speed sensor.
Perfect example. You're driving, you hit the brakes hard. But the noise from the newly updated inverter is now swamping the signal from the wheel speed sensor. The ABS computer can't hear the sensor anymore. It thinks the wheel is locked up, so it does its job and releases the brake pressure.
So my braking performance is suddenly reduced, and the root cause was a software update that was supposed to give me more range. That is terrifying.
It's the new reality. So what's the strategic answer? You obviously can't recall every car and retest it in a physical chamber every time you want to push a one-line code change. You go bankrupt.
So you have to virtualize the compliance?
You need what we call lifecycle EMC compliance. This is where that digital twin we built for development becomes an operational tool. Before that OTA update gets pushed to the fleet, the new software code is first run through the executable digital twin.
You perform a virtual regression test.
You simulate the new switching patterns against the validated electromagnetic model of the car. The simulation predicts the new EMI profile. If it shows a new noise spike that violates the limits or interferes with a known sensitive frequency, the build fails. The software is not allowed to be deployed.
This implies a massive cultural and organizational shift for automakers. It means the software engineers writing code in one building need to be in constant communication with the EMC physics experts in another.
The traditional silos between the software team and the hardware team have to be completely demolished. If your code can change the physics of the car, then a physicist needs to be in your code review process. The EMC engineer is now a final gatekeeper for software deployment. That is a radical shift in the power dynamics inside an OEM.
A true process revolution. It's not about buying a new tool, it's about drawing a completely new organizational flowchart.
And that, as we all know, is often much, much harder to implement than any new piece of technology.
Okay, we have covered a huge amount of ground here, from microarsing inside a ball bearing all the way up to the geopolitics of Chinese versus UN regulations. Let's synthesize this for our client. Let's bring it home. We promised a MEC report. What are the 4 key actionable recommendations they need to be writing on their whiteboard right now?
Recommendation 1. Don't fight the global divergence in regulations. Embrace the strictest standard as your internal benchmark. That means you adopt the Chinese GBT 18655-2025 test setups for your e-axles, regardless of your target market. It's a better, more rigorous engineering test that will future-proof your designs.
Find the leak in your lab, not in the field. Got it. Number 2.
Recommendation 2. Invest in the technology required to meet UNR 10.07. That means you absolutely need FFT-based receivers to accelerate your testing. Time is money, and you need to be making a serious investment case for reverberation chambers. The 6 gigahertz world is just too complex and chaotic to rely solely on directional antennas. You need to stir the waves.
Makes sense. Recommendation 3.
Implement the hybrid lab strategy. Don't pour every dollar of your capital budget into building more big, concrete bunkers. Use flexible, mobile test beds for your R&D and component work to keep your expensive chambers running and collecting data 24/7. Maximize your asset utilization, and make sure your big, fixed rigs are built to be invisible. That means ultra-low noise floors and non-invasive pneumatic robotics.
Okay, and the final crucial recommendation, number 4.
Operationalize your digital twin. It cannot just be an R&D tool. It must become a core part of your software release process to manage the OTA risk. If you are building and selling a software-defined vehicle without a virtual EMC sign-off gate for every single update, you are, to be blunt, driving blind. You are one line of code away from a multi-million-dollar recall.
That brings us to our final provocative thought, the big why does this all matter moment.
You know, for years, we in the EMC community have had to fight for budget, for attention. The problems were seen as annoyances. Static on the radio.
Hey, AM radio buzzing when you accelerate. We've all heard it. It feels like a trivial problem.
Right. Who cares? Nobody listens to AM radio anymore. It was a comfort and convenience issue. But in the emerging age of autonomous driving and full drive-by-wire systems, we are not talking about radio static. We are talking about the fundamental signal integrity between a digital brain of the car and the physical muscles of the car.
The stakes have changed from annoyance to life or death.
Completely. I want you to picture this. It's 2028. A 60-ton, fully autonomous, all-electric semi-truck is cruising down the highway at 65 miles per hour. No driver. It passes a new, ultra-powerful 5G broadcast tower.
A huge blast of 6 gigahertz energy washes over the truck.
If that truck's EMC shielding isn't perfect, if there's that 5-centimeter gap we talked about in a door seal, and that wave of energy gets inside and couples into the drive-by-wire braking controller.
It could interpret that noise as a valid brake command or a phantom obstacle detection.
Or it could corrupt the real brake command. It could cause the controller to reboot. It could cause a sudden steering jerk. EMC is no longer about comfort. It is about preventing that 60-ton truck from executing a random catastrophic maneuver at highway speeds simply because it drove through an invisible field of radio waves.
The noise is now a matter of life and death.
That's the bottom line.
That is a very sobering thought to end on, but it perfectly highlights why this entire conversation is so critical. This is not a niche engineering discipline anymore. It is core to safety and reliability. To our clients listening today, the engineers, the managers, the strategists trying to navigate this, good luck. The physics are definitely getting harder, but the tools and the processes are, thankfully, getting better.
Just remember the framework. Start with a top-down strategy. Don't get lost chasing individual component failures. Look at the whole system architecture. Get the physics right at the source. Manage the risk through the process, and the compliance will follow.
This has been the Deep Dive Consulting Team. Review the metaphorical slide deck, and we'll catch you on the next engagement. Signing off.
Goodbye.